We continue here with static equilibrium, and we are going to meet beam problems in this video. And when we solve these, we are going to use the conditions of static equilibrium, which namely are the net force must equal 0 and the net torque on the beam must equal 0, which in terms of a beam problem, which has weights on the top of it and it's being supported at certain points on the bottom, what the net force being 0 means is that the ups have to equal the downs. The forces that are acting up need to be numerically equal to the forces that are acting downward, and the net torque being 0 means that the clockwise torques have to be numerically equal to the total of the counterclockwise torques. And the other thing that is important with beam problems is we need to put in somewhere, and we'll show you how to do this, an imaginary pin, an axis about which we're going to find all of our torques. Let's show you how to do that. Here we have a beam, has several point loads on it, and what we want is we want to know what is that reaction right there. I'm going to call it reaction at A. That's the force that's holding up that end of the beam. And what's the reaction over here? I'm going to call that RB. That's the force that's holding up the beam on this side. If this is a symmetric system, RA and RB will be equal. But you can tell just by the picture that it's not quite symmetric. We are, in this case, going to assume that the weight of the beam is negligible. So we're going to sum the forces up and down, and we've said that the ups have to equal the downs. The ups are RA and RB, according to our drawing, and the downs, we could write them out separately, 300 plus 200 plus 240, but it's the total that's important, and I think we can do that in our head, can't we? 740. So that's the first condition for static equilibrium. That's not enough, though, because we have two unknowns and we only have one equation. So we need to write another equation where we're going to sum the torques. And this is where we have to pretend to put an imaginary pin in somewhere. So I'm going to put this imaginary pin right there. I'm going to pretend that I'm holding that beam in place right there. And you can see then all of these other forces, the 300, 200, 240, and also RB, those contribute torque relative to this pin. RA contributes 0 torque because it's pushing right on the pin. You can see that RB, if it had its way, if this is the pin on the left side, RB would tend to rotate the beam counterclockwise. The 300 and the 200 and the 240, those would tend to rotate the beam clockwise, wouldn't they, if that was the pin on the left end? The clockwise torques need to add up to be equal to the counterclockwise torques. I'm going to sum the torques about point A. Let's do the counterclockwise torques first. Force times lever arm. What's the lever arm for RB? It's the distance between the pin and RB, which is 12. That's the only counterclockwise torque. The rest are clockwise. Let's put those in. Force, which is 300. The lever arm is 4. We also have a 200 Newton force, and what's that lever arm? 6. Everything is measured relative to the pin. And we have one more, and that's 240 newtons. What's the lever arm for that? I think 10. So what does this come out to? This is 1200. This is another 1200. And this is 2400. So that means RB times 12 is equal to 4800 newtons. We can't always do this in our head, but this one I think we can. RB then will be 400 newtons. And it acts in the direction that we thought it did, up. What about RA then? Well, now we use our first equation, and we say, well, if RB is 400, then RA must be 340 newtons. And since that came out positive, that also acts in the direction that we guessed that it acted, which was upward. All right, let's end this by answering this question. When solving beam problems, why is it convenient to choose the rotation point, or the axis, the pin, along the line of action of one of the unknowns? And we said this when we were doing this problem, but in case you missed it, that unknown is thus omitted from the summing of the torque equation. In fact, it's on the screen still. You can see when we wrote our torque equation, RA was not in there, which was nice because that was one unknown that we didn't have to deal with. Whenever you put your imaginary pin in there, it's a good idea to put the pin in line with one of the unknowns. Now, we could have put the pin in over here with RB, and we would have solved for RA first, and we would have gotten 340, and then we would have said, oh, then RB must be 400. So it doesn't matter where you put the pin, as long as you do the problem correctly, you're going to be good to go.